Okay, we're going to look at theoretical versus experimental probability. We have our question written out here, so I'm going to read it over once, and then I'm going to highlight important information and try to do a comparison between the two things that it's asking us. So the very first line says 9 dice are rolled. The outcomes, should be an S, the outcomes are listed. And there are your outcomes. They have a 2, a 4, a 2, a 5, a 4, a 2, and then the rest of the dice are 6. So the very first question is, what is the experimental probability of rolling a 2? What is the theoretical probability of rolling a 2? So let's get our important info here. There are 9 die. That's actually really important. These are the outcomes right here. And the question, first one asks us about rolling a 2 with experimental probability. And the second one asks us about theoretical probability of rolling a 2. First thing I'm going to do is actually represent... I'm going to actually represent a space for each of the die that are rolled, or the dice. So because there are 9 of them, I'm going to have 9 placeholders. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm glad I counted it out loud, because I'm sure counting is hard. Okay, and then what we're then going to do is write down the values that were represented with each of the dice. So the very first value is a 2. I'll write it out numerically. I mean, I could draw it as a die, but that's just going to take me longer. So the second die had a 4. The third one had a 2. The fourth one had a 5. The fifth one had a 4. The sixth one had a 2. And then it said the rest are 6. So the next 3 are 6, 6, and 6. So there you go. And I mean, I could draw out all of the faces of the dice there, but those are the numeric values. So that's what's really important here. And again, these just represent the 9 dice that were rolled. This is our experiment. So in order to figure out our experiment, we have to figure out how many times we conducted the experiment. And because there were 9 die, or 9 dice, the denominator is out of 9. The second thing we got to check is how many 2s were rolled. Well, we have 1, 2, 3. Okay, so the numerator represents the number of times we rolled a 2. So there are 3 of them. So it is 3 out of 9, or you could write it as, I'll do it in green as a final answer, a reduced fraction of 1 over 3. So the experimental probability in this experiment is 1 over 3. Now, the theoretical probability is a little different. Theoretical probability has nothing to do with any of our experiment. It has everything to do with the device we're using. So because we're using dice in this situation here, dice is a cube, or a die is a cube. Okay, and the number of faces of the die represent the numbers you can get. So you can have like a 1, a 2, a 3. I'm going to open this up into a net, and that's where you take a 3-dimensional shape and you just kind of lay out all of its faces. Okay, and there are 6 faces. So we have 1, 2, 3, 4, 5, and 6. So there we go. We have our 6 faces of a die, which means the possible outcomes are, I'm going to write them out, 1, 2, 3, 4, 5, and a 6. That's it. Now, we said there are 9 dice that were rolled, right? So that would be the first one. Then we have the second, and we go all the way to the 9. And we know that every single die has the exact same makeup. So what that means is the other 8 die that we use are actually not important for our experimental probability. We just have to look at one of them. So when we look at one of them, we know there are 6 sides, okay? So the 6 sides, or the possible outcomes, is our denominator. It's out of 6. How many possibilities could end up in a 2? Well, there's only one side. So because there's only one side that can end up in a 2, we get a 1 in 6 chance. So our theoretical probability is 1 out of 6. So you're going to notice that the experimental probability and the theoretical probability are not quite the same. And what happens is, the more experiments that you conduct, the closer this probability should get to the experimental, or to the theoretical probability. So our theoretical probability is what it should be, and the more experiments we conduct, the closer we get to that theoretical probability.